What we're going to talk about today is more of the hardware details. You might remember that last time we introduced this nice, pretty, complicated picture that says this is all the stuff that's in an operating system, usually. And it's a nice sort of high-level schematic view of all of the different components that you might have to implement and think about when you're building an operating system. And we started talking about a couple of different things that were really important for implementing a good operating system. And one of them was having some kind of protected mode execution. So I have to have a way of doing user mode and kernel mode to separate between those two by hardware. And then we also talked about isolating processes from each other. And so that required this virtual addressing mechanism. And so today what we're going to do is the first part of the lecture. Yeah, so this is talking about kernel space. Okay. So basically everything below the system call mechanism is in kernel space so that it can't be accessed directly by user processes. And so then the applications live up here. And obviously they can do things, but the OS is protecting itself. They also can't necessarily bang on each other because you don't want to have that either. And so what we're going to do is we're going to sort of extend this list of hardware requirements for a good, reliable OS today. That's the first thing that we're going to talk about. And there's a lot of technical details in the lecture, but I'm going to try to gloss over a lot of those and just point out the most interesting ones. Partly because you've seen them, and partly because it's not really crucial to dive into all the gory details right now. So first thing was, how do we actually get from user mode code into kernel mode OS? And the simple answer that most operating systems use is they have some special kind of instruction, typically called a trap instruction, that allows you to switch from user mode to kernel mode in a very controlled, specific, predictable way. Okay? And so I say here a trap instruction. It's funny, we actually saw two of these. Who took CS24 last year? So a lot of you did. So you remember that, since we went to 64-bit, in class we talked about the int instruction, which is the old school way that it was done. In fact, I talk about it here. At some point I talk about, probably next slide, I talk about int. But last year we actually used a different one, syscall. Syscall allows you to transition from user mode into kernel mode. And there's a second one on x86-64 called sysenter. So different OSs, different hardware platforms will have different kinds of trap instruction. But we just need some way of getting from the user mode code into the kernel mode code. Okay, so like I say here, intentional software generated exception or interrupt. So the OS will provide handlers. Okay, so this is really talking about like int instructions, that kind of thing. But the bottom line is the kernel has to do some kind of setup at initialization time to make sure this mechanism will work properly. Okay. Now, there's a couple of benefits from this. Because remember, we're talking about protecting the OS from the user application. But there's a second benefit to this, which is that we may have subroutines whose locations change from version to version of the OS. So this routine grew because we wanted to add features, and that pushed other routines out. And so we really can't have applications accessing those things directly by some address or offset or something like that. So again, we have another level of indirection. And you see that kind of thing a lot. Basically, when you design these systems, you have to worry about maintaining binary compatibility because the application is probably fixed, probably frozen. You don't want to rebuild it when you change your OS or upgrade it. And so having that level of indirection is really helpful. That's the other big benefit that we get out of this. And then obviously the one where we can prevent applications from doing naughty things. And there's a lot of interesting ways in which this can go wrong. We'll talk about some of those when we get into the syscall lab. Because there's things that you may not actually think about. We're writing a program to be malicious in specific ways, but there's some very clever things you can do to try to exploit an OS. And the OS has to guard against all of those things. Okay, so IA32, again, if you happen to have the good or bad fortune of doing CS24 last year, we did x86-64. So IA32 is the 32-bit version of that. And basically, IA32 always uses int. Or I should be careful about that. It doesn't always use int. It can also use sysenter or syscall. But in general, int is a reliable mechanism. And on 64-bit, you only use int. 32-bit program. So anyway, whatever, we won't get too caught up in the details. But we use the int instruction to get into the kernel. And so, for example, Linux uses int 80 to get into the kernel. Different OSs will use different interrupt numbers. Like Windows uses 2E. I think Pintos uses 30 hex. Don't quote me on that. We'll get to there when we get to assignment 4. But anyway, we have different stacks for these different operating modes so that the kernel stack doesn't get affected by misbehavior of the application. So the application fills its stack. We don't want the kernel to necessarily be affected by that. Okay, so all of this kind of stuff, again, detail that we don't really need to get into. This happens to be how Linux does argument passing. It passes through registers. It actually does that in 32 and 64-bit mode. Pintos happens to pass things on the user stack, which is weird and a little bit gross. But you'll see that there's a variety of ways that you can actually pass arguments. Okay, let's see. The way that these things are dispatched is through the interrupt descriptor table. So again, we don't have to care about this too much. You'll actually have to care about it a little bit in the second project because you'll have to set up an IDT for various interrupts to be dispatched. Because when somebody presses a key, how is your program going to find out about it? Well, an interrupt will fire. So you'll need to have a handler for that. How do you know when a timer goes off? You'll get an interrupt for that. So this interrupt descriptor table has an entry for each of the interrupts that the processor is capable of dispatching. And then that IDT entry contains details about where to go and other information about it. Okay? So protected mode, you have 8 bytes per entry. Again, this is 32-bit. If you have a 64-bit system, then each descriptor is 16 bytes. If you're doing the old x86 stuff, then it's 4 bytes. So it varies based on the configuration of the processor. But anyway, so that gives you the address of the handler and a few other configuration details that the operating system would prefer to have. So program issues int n or a hardware interrupt occurs, then basically the processor takes the corresponding entry from the interrupt descriptor table and says, here's the routine that I need to call. But it also does a little check here, a privilege level check, which again, not really critical because usually we go from user mode or ring 3 into kernel mode ring 0. So it basically says, as long as you're in at least ring 3, you can go to ring 0. Okay, so that's the basic idea here. Let me see what else we talk. Yeah, so there was a whole bunch of stuff, and we talk about this a little bit in CS24 of all the things that are saved since we have to switch stacks. I should say if we switch interrupt levels, we switch stacks. And there's other details that are saved. And so the IRET instruction allows us to roll all of those things back. So you'll see an int instruction at the end of the interrupt handler. You'll have an IRET. Pretty straightforward. Okay, so a few details there. Yeah, the only thing that's really interesting here is that obviously the processor, when it boots, starts out in kernel mode so that you can actually configure it. And so that's kind of the important step there. One of the lectures that comes next week, which I won't be here for, but there's a recording of it, is a discussion of the bootstrap process. And you'll see that it's actually a multi-step process. The very first step is run like 16 instructions at the top of memory, and then that jumps to the FiOS loader or the EFI loader, and then that thing runs, and that pulls the next stage off the disk, and you go through this whole process. So all of that happens in kernel mode, or the highest protection level of the processor, so that the OS can set all this stuff up. And then when it's ready, it finally switches into user mode to say, okay, user, we're all set for you, everything is configured, and then off you go. Okay, so that's another little implementation detail here. Are there any questions? Okay. Again, you really don't need to care too much about this. You'll care more about it in the second assignment, but actually I give you a lot of helper functions and things like that to help you with those things. So some of them you'll have to implement, but they're pretty straightforward. Okay, so exceptional control flow. This just really gets into the general category of things, and again, we talk about this in 24, so we won't spend too much time on it. So traps, intentional exceptions, software-generated exceptions that get you into the kernel. You have interrupts, which tends to be that when we say this interrupt term, we mean hardware interrupts. So timer goes off, disk controller goes off, keyboard says I have a key, things like that. Basically, it's hardware telling the OS there's some information you may want to handle. Okay? So the OS can deal with it quickly and then go back to whatever makes sense to do next. Okay? Now, both traps and interrupts have this characteristic that they return to the next instruction. I think that's pretty obvious. The only other thing that I'll mention here for interrupts is sometimes people wonder about the interrupt dispatch mechanism. It never interrupts an instruction. So let's say you're doing a divide in an IDIV instruction or something like that, and it takes hundreds of clocks. Well, the interrupt, if there's an interrupt pending, it won't be delivered until the current instruction is completed. Because it would be really bad to be able to interrupt an instruction. So interrupts are always dispatched in between instructions. That keeps things cleaner and simpler. Okay, then you have faults. Oh, yes, question?
What's like the time sensitivity of interrupts? Like if you get an interrupt on a process that is not currently running, do you have to switch? Is it like you have to switch that context and handle it now, or can you wait till you switch back?
That's a really good question. Like, if you have an interrupt so we're saying that a hardware interrupt occurs and there's a particular process that cares about it, right? That's the scenario. So, the difference between the time of the interrupt occurring and the code that cares about it actually running is called the interrupt dispatch latency. And we'll talk about that in the future. But most OSs don't really care about making that time period as short as possible. It's really only in hard real-time OSs that you try to get that dispatch latency as small as possible. There's a number of techniques that are used to resolve that. And one of them is actually being able to interrupt the kernel. Because a lot of times, processes may be doing things, and it's always possible to interrupt a process because it's in user mode. It's like at the lowest level. It's like it's just a worker. It can interrupt it at any time. But if you're in the kernel, some OSs allow kernel execution paths to be interrupted. And so that reduces the interrupt dispatch latency even further. So we'll talk about some of those strategies in a future lecture. Okay, faults. Usually unintentional, almost always unintentional. So typically it's caused by executing a certain instruction, and so the hardware signals to the OS, hey, there was a fault, maybe you can recover from it, and so the kernel tries to resolve it. And if it can, when we return, we go back to the instruction that caused the fault, aka the faulting instruction. Sometimes you'll hear people describe it that way. So, this is kind of a fun one. This is where all your complexity lies. You have your seg faults. I tried to dereference null, or I just decided to run a page of my program code and the page isn't loaded from disk yet, generated a fault. I try to access a page on the heap that hasn't been allocated to me yet, that generates a fault. So some of these situations are recoverable, but not all of them are. And so the challenge is for the OS kernel to distinguish between those different scenarios. And so this is a fun one. We won't really tackle that until Project 5, which is kind of nice because up till Project 5, any fault means a bug. But then after Project 5, faults become normal scenarios as well. So you need to be able to handle them. But anyway, if the OS can recover, then it returns to the current instruction. The last kind of exceptional control flow in the processor is an abort, and basically this is when the hardware detects an issue that is not recoverable, and it just halts the processor. Okay? Tends to be that you need to do a hard reset in these situations. So power cycle, push the big reset button or something like that. Okay, so we need some, I'm going to skip over this one. Oh, this is kind of a fun one. I guess I'll tell you about this one. These are basically the exceptional control flow mechanisms that we have on the hardware that the OS needs to be able to deal with. Okay, so IN32 has this thing called double fault. Let's say that we have a page fault. Somebody dereferences null or somebody accesses a page that needs to be loaded, and something happens during the fault dispatching. So I call the page fault handler and the permissions are wrong. Or I call the page fault handler and the page fault handler false. These are bad scenarios. Okay? So here's the example. User is running along, an interrupt occurs. The CPU looks up in the interrupt descriptor table. Maybe the IDT entry is a bad instruction. So you can imagine like all kinds of horrible things could go wrong in this mechanism. And so the CPU tries to invoke the handler, and another fault occurs. So this is called a double fault. Does this seem like a situation that an OS should have occur? Usually double faults indicate bugs in your OS. So you would not expect that something like Windows would double fault. You wouldn't expect that Linux would double fault or OS 10. But you probably will have your own OS double fault, and maybe a lot. Now, another scenario, yeah, that causes double fault. So you have a page fault, and then there's a page fault trying to dispatch to the page fault handler. So if you have a page fault dispatching the page fault handler, who resolves that page fault? Page fault handler can't do it. So this is another scenario with a double fault. Okay. Now, it gets worse. Like I said, these are operating system bugs. You can register a double fault handler, though. I don't know what it would do. Would it reset the OS? What would it do? I don't know. Maybe it would try to reinitialize things so that we could try to get things going in the right direction again. But it is possible that during double faults, dispatching another fault occurs. That's called a triple fault. What happens in this situation? The processor gives up. Okay, so this is what happens on the x86 processor. If it hits a triple fault, it just halts. So this is another example of an abort, and this is one you will come to hate when you see, like typically what you'll see is the emulator in an infinite reboot cycle. Okay? And usually it's because something happens, you triple fault, it restarts, goes, does the same thing again, triple faults, and restarts again. So that's a fun thing to deal with. Oh, OS programming is really fun, guys. I promise you. Okay, any questions? So there's faults. There's a little bit of discussion of exception handling. So why are we discussing this? Well, because this is another one of those hardware capabilities that really is required if you're going to build a useful OS. One of the things that's interesting about this is just having a trap mechanism allows you to build, and I should really say like a trap mechanism and a hardware interrupt mechanism. Having those two things by themselves is sufficient to build a pretty reliable OS. But the problem is you still only can build cooperative multitasking. And so there's another facility we'd like to have in the hardware, which is some kind of timer interrupt that we can configure only from protected mode, and then we can use that to preemptively take back the processor. Because remember, processor is another resource that the OS has to manage. So cooperative multitasking, processes voluntarily relinquish the CPU. The only problem is if you have a bug that never does any I/O. So I don't know if you guys remember the things that allow a CPU to be yielded. We talk about this in CS24. If a process blocks or yields or terminates, those are the three things, and that's a good thing to sort of keep in your mind when you're thinking about process scheduling. A process can block on a long-running I/O. I read the keyboard. There's no data. Okay, I'm bored. Go do somebody. Go run some other process. Okay? Or I intentionally yield the CPU, or I terminate. Those are the three things that allow the CPU to be scheduled to somebody else. So, like I say here, if you have a program that doesn't do any of those things and you have cooperative multitasking, then you never get the CPU back, and you're stuck. The whole OS will appear to have hung. Interestingly, there were quite a few OSs that did cooperative multitasking from the beginning. And they were perfectly usable because it turns out that most programs, block or yield a lot. And then eventually they terminate. And so that allowed things like I say here, Windows before Windows 95. Windows 95 was the first preemptive Windows operating system. I used Windows 3.1. You probably never have. It was fine. Mac OS before OS 10, or OS X now, as it's called. So that's another one that was cooperative, and it worked fine enough. Okay. Interestingly, like I say here, not Unix variants. It turns out that Unix has been preemptive pretty much from the start. So Unix has been designed to be preemptive multitasking from pretty much the very beginning. So this is where a hardware timer facility solves this problem, and it allows us to take back the CPU even if a process does not block, yield, or terminate. Okay, so that's preemptive multitasking. Okay. And the nice thing is that all good OSs, like all generally widely used general purpose OSs now have preemptive multitasking. So if you have a process that decides I want to sit in an infinite loop and do nothing else and talk to no one else, then it doesn't cause the whole system to really fail or struggle along. Okay, any questions about multitasking? Okay, we're going to spend a lot more time talking about this in the future when we get to the threading project, but this gives you sort of the general overview and the motivations for certain hardware requirements. Okay, APIC. I'm not going to really spend any time talking about the APIC. Just be aware that there's this thing called the Advanced Programmable Interrupt Controller, and this thing is really clever. Like, you can schedule and prioritize interrupts and how they're delivered and so forth, and the operating system needs to talk to the APIC to configure the interrupt delivery, which interrupts are ignored, which interrupts are used, who handles them, and so forth. Okay? So you can see you have a lot of useful things. So timer interrupts are on the local APIC, thermal, so your processor gets too hot, rather than it exploding, which they used to do. It was really cool. People take the heatsink off the CPU and it go pop, and it would be just gone. But now they just stop. So performance monitoring and so forth. So you have various things that can be delivered. The I/O APIC is what talks to external devices. So that's all really neat and good. I'm going to skip over this stuff, and I'll explain why momentarily. Perhaps the only interesting part of this is just how multi-core systems work. So each processor has its own local APIC, because each processor needs a timer. You need to be able to set up your preemption and so forth. But each processor doesn't need to have its own line to the disk controller. That doesn't make any sense. So there will be one I/O APIC that talks to the keyboard and storage devices and things like that. And that interacts over a bus with the local APICs on the various processors. Okay. Now, the reason why this is cool is because these processors now have a means to communicate with each other. So a processor can actually send this thing called an inter-processor interrupt to another processor. And we talked briefly about this in 24. What if I have a process and it's running on one CPU, and I want to kill -9 that thing because it's not stopping or it's not doing what I want it to. And so I'm on another processor. I can kill that process, and the OS will send an IPI to the other processor saying, hey, stop what you're doing because we need to have a talk. So you can do things like that relatively easily. So you can see that as you get into multi-core, you need to have this communication mechanism between different processors so that one processor can tell other processors, you need to pay attention to something. Okay? The other neat thing about this is that you can configure the I/O APIC to round-robin interrupt delivery. So for example, if you want to have all your processors have basically the same interrupt latency, then you can just have the I/O APIC round-robin to the various processors. Or, alternatively, you can have one processor devoted to interrupt handling and leave the other ones just focused on application execution. Okay? So there's a lot of power and a lot of flexibility at this level. Okay, any questions? This is thankfully not the world you will have to live in, because what happened is back in the 8086 days and 8088 days, we had what was just called the PIC, Programmable Interrupt Controller, and it's a very simple little system. It can handle up to 14 hardware interrupts, and that's what Pintos uses. That's what you'll use for the second assignment. So this is mainly for your edification. This is what modern operating systems use. All the modern operating systems running on x86 have to know how to talk to these things. Okay? They're complicated beasts. All right, so we talked about this in CS24. So just as a reminder, remember that having hardware interrupts allows us to perform these long-running operations and then context switch away. So this is what happens when a process wants to read, wants to write, and then they block. So great time to do a context switch. And then the OS kernel can receive a hardware interrupt when it's time to go back to a process. Okay? And just as a little point of note here, this is where you can think about whether you care about interrupt dispatch latency or not. Like most general purpose OSs, when that interrupt goes off, well, the process was already waiting. There's no rush to wake it back up and let it start progressing again, unless it's at a high priority. So typically, the OS scheduler can think about, do I want to wake somebody up, or can I just keep doing what I'm already doing when that interrupt goes off? So you'll see some of that in the scheduler lab. There's some cool interactions that you'll see in the scheduler lab. Illustrate a lot of these points. Okay, so this is the point. I know this is a lot of detail, and I hate going into too much detail before it's necessary. But these are basically the facilities and the hardware that we need to build sort of a modern OS with modern OS capabilities. So at least dual mode execution, some kind of process address space isolation, so virtual memory management, some way of getting from user mode into kernel mode. Obviously, if we have this, we have to have this. We have to have some mechanism for software interrupts, or some, like this really goes here. But software interrupts also help us with faulting. So that gives us the ability to overcommit on physical memory and provide this virtual memory abstraction. The virtual memory is much larger than physical memory. And hardware interrupts allows us to do background I/O and allow other things to occur. And then a hardware timer facility is necessary if you want to do preemptive multitasking. Okay? So this is kind of your ingredient list for building a good OS. If you happen to have a processor that's missing some of these things, well, you're limited in what you can do. And that's actually, I'm about to beat up on DOS. And there's a reason why DOS was so simple. It's because they had a processor that didn't have dual mode execution, so it definitely didn't have trapping, and it had very limited, it had basically no virtual memory management as well. We had a hardware timer, but there was no protection of it, so the OS was at the mercy of the software that it ran. So yes?
If you did like int and then something other than 80, would that be effectively like signaling some other hardware interrupt or something?
That's a good question. What happens if you do int with something other than what the OS sets up? Well, if you have a good OS, then basically the OS is going to install an interrupt handler for every single possible interrupt on the computer. And so, for example, if you said, I'm going to be crazy and do int 81 because it's one more, then the kernel would receive that and say, this process is acting dumb, let's kill it. So that's one scenario. You can try to invoke hardware interrupt handlers, but I think in general, the OS kernel will look at the device and say, no device is ready, and so it'll just ignore it. Because I think that's basically all the kernel can really do in that situation. One of the little side notes about this is when you have an interrupt handler, like let's say that you have hardware devices mapped to like int 40 or something like that, which is not uncommon, then what happens is multiple devices are mapped to that interrupt handler. And so when a hardware interrupt occurs, the kernel has to go through and ask all those devices, do you have something for me? Do you have something for me? And so it responds to the devices that are ready. And so that's why I believe that if a process were to invoke that through software, the kernel would just be like, I don't have anything to do, so I'm going to go back to whatever. There's probably other clever things that the kernel can do as well. It's not a question I've explored in great depth. Any other questions? All right. So let's see. So yeah, we'll discuss those. Yeah, and sadly, a lot of detail. Like I said, assignment 2 is about the goriest you'll get as far as all of this stuff comes. And I walk you through all of it, and we don't do it with the APIC, we do it through the PIC. So it'll be a relatively straightforward process. But you'll get a taste of how grungy it is to talk to hardware. Okay, enough of that. What I want to do for the remainder of this lecture and the next lecture is talk about OS architectural patterns. Like probably some of you have heard of microkernels. Like microkernels are somehow good, and the opposite of microkernel would somehow be bad, or things like that. So you've probably heard things like this before. So we're going to talk about all of those things. But there is one common theme through all of this, which is separation of policy and mechanism. Policy tends to be what you want to do. Mechanism tends to be how do I do it. And we want to separate those two things. Like I say here, policy is what needs to be done. So these are some examples. Which virtual page should I evict? What process should the OS run next? So you can imagine you have a paging policy, and that makes that decision, and you have a scheduler, and the scheduler decides what process should run next. Then you have mechanism, which is how do you do the thing that you want to do. Okay? Now, the detail here is that the mechanism is tied to the computer hardware. And therefore, it is highly unlikely to change once you set up a system. So how do you save dirty pages? How do you talk to the CPU to say, hey, your page table's changing? How do you save the current context? That depends on what registers we have, what registers we care about preserving, and so forth. Okay, so you can see how mechanism wouldn't change. So policies change all the time. In fact, you may even configure your OS to have one policy over another. Now, it tends to be less common in a general-purpose OS like Linux or Windows. You can't really change the scheduler very easily. You kind of have to do some low-level things to do that. But when it comes to things like your mobile devices, anybody have an Android phone here? So, anybody familiar with the governor thing on the Android phone? So there's this little component called the governor, and that chooses the speed that the processor should run at. That thing is policy. How you actually change the CPU speed on various devices is the mechanism, and obviously it's specific to a device. But when I used to have an Android phone, that was one of the things I could configure if I wanted to. Well, I want to do this, or I want to set the priority to be that. Okay? So that's a really important principle. You'll see it all over. It's important as well for in your own OS implementation. Okay, then there's various structural patterns. So the simplest one, probably shouldn't call it the simplest one. The most basic approach that one can take is called the simple structure, where you basically don't have any modular design. You don't really have any constraints on what can see what or what can access what parts of the OS. So it says here every part of the OS can access every other part. Okay? And that usually means that everything can access computer hardware as well. Now that may be okay for a little tiny, like an embedded system, or a small OS that you're building on your own. But hopefully you can imagine where this could start going wrong really quickly. Because once it gets really all, we call it a big ball of mud or something like that, it's like it starts getting intertwined. And it's very easy to have bugs in one part that are caused by a whole bunch of other things in the system. Okay? So yeah, it usually happens when you don't give any attention to design and architecture. Okay? Susceptible to OS bugs. That's a given. Also susceptible to application bugs. Okay? That's not entirely true. We'll actually talk, usually simple structures exist in the context of no protection levels. And so that's why we say that it's susceptible to application bugs as well. Tends to be easy to compromise because there's oftentimes little bugs lurking that can easily be exploited. And it tends to be difficult to extend the functionality because usually if you don't have a modular system design, you can't see where things should fit in. And you try to fix one thing and it has far-ranging implications. So DOS is the classic example used for simple structure. Like I said, this was written for a very limited processor, so that's why it was so incapable of preventing so many abuses. It's not really any surprise. Windows 3 was a big step forward, and then Windows 95 was a big step forward. So it's not like they've all been bad. It's just DOS was limited by its context. This is kind of a picture that you can imagine. Anything could access just about anything. I want to write a program. Well, I could talk to resident programs. Those were ones, they were called TSRs. They would stay in memory and take care of things for you. You would have device drivers. Well, the application can talk to the device driver. You have BIOS drivers, the firmware on the computer. The application could talk to that, frequently had to. And then the application could even talk directly to the computer hardware. I did all those things when I had a DOS computer. It was really fun. Okay. The only problem is that it would make it difficult to have a highly reliable system, and it was really easy for one app to mess things up for other apps. Okay. One of the things that frequently happen on these computers, thankfully it basically never happens now. Well, I suppose that rootkits are kind of an example of this, but this was really ubiquitous back in the day. DOS would have a hardware interrupt, a software interrupt that could be used to call into the DOS services. Well, a virus could install itself as the interrupt handler for DOS, and then just filter the information going into the OS and filter the information coming back out. So basically, they could make it look like they completely weren't there. Okay. They were so cool. I love that stuff. If anybody's curious, I'll show you some source code from some of the old stealth viruses. They're really amazing things. And one of my favorite was actually a virus that could tell when it was being debugged. So on the 8086 processor, you have int3, which is a different instruction encoding than the other interrupts. It's usually CD, hex, and then the interrupt number. Int3 was just CC or C3. I can't remember which it was. But you just have this one byte, and you plop that in if you wanted to have a debug breakpoint, and it would set certain registers on the processor. And so this virus would check to see what this register state was as it was running. And if it was running inside a debugger, it would actually copy itself to a different memory location, disable the debugging facilities, and go on its merry way. So it would actually hop out of the debugger. Wild stuff. You can't do that anymore because you're limited by the process constraints now on real OSs. But DOS didn't have any of those constraints, so you had all kinds of things that could go on. Okay, Unix. Well, thankfully it was more well-designed than DOS was initially. Also, they had better hardware facilities, so they could think more carefully about how things were designed. But they tended to be more structured. And so you did have a division, at least, between the kernel and the applications, but the kernel itself was still kind of this big mass. So we call this a monolithic kernel. A monolithic kernel is a large amount of the OS actually runs in kernel mode. And there tends not to be a lot of structure to it. Okay? So again, bugs can wreak havoc if you have a bug inside of a monolithic kernel. Okay? So hopefully you're already starting to think about this question, which I'll just implant in your mind if you have not. Monolithic kernel. What's the kernel? It's the stuff that runs in kernel mode. So the following question should be, well, what has to be in kernel mode? Does everything in the kernel actually have to be running in kernel mode? And if not, can we start pulling some of that stuff out? Monolithic kernels are kind of at one end of the spectrum. They have more things in kernel mode than is strictly required. Maybe a lot more. Your printer driver. And now your printer can crash your computer. Or I should say your printer driver. Okay? So that was common in early Windows days, by the way. Okay, so kernel subsystems can access each other, so that's not great. The reason why people like it, though, is because it's fast. Switching from user mode to kernel mode takes time, especially if you're switching stacks, which almost always you do. If you're going through the interrupt dispatch mechanism, that's also slow. But if you're just doing a whole bunch of stuff inside the kernel and you're all in kernel space and everybody's running in kernel mode, really fast. And so this is why people like monolithic kernels. Okay? So you'll notice this little point here. We'll talk about this more next time. Many modern OSs actually tend toward the monolithic end of the spectrum because it happens to be fast. And people want fast computers. Okay? Okay, next design approach that has been explored is called the layered structure. Basically, this is a highly structured approach that one can take to operating system implementation. And so this was actually, this guy you may have heard of, Edgar Dijkstra, did a research project using the layered structure. And wait till you see the name of the OS. It's really annoying. So, but you'd have layers, and each layer would basically only talk to the immediately I don't even know how to say this, the layer that was immediately beneath it. So you'd have this direct interaction. You wouldn't be tunneling through multiple layers, and each layer would provide services, and then the next layer above it would be interactive. So very clean design. Okay? And so basically this allows the individual layers to be tested really effectively. And so you could basically make a layer bulletproof, and then put another layer on top, and then you can make that layer bulletproof. Very reliable way to create a bug-free OS. Okay. There's the name, the OS. So the reason why it's called the OS is because it's the initials of the, I don't even know how to say this. I'll give you the English name. It's the Eindhoven University of Technology is what THE really stands for. And So Dijkstra worked on this project in 1965, and you can see it took a while. But it was a batch processing system with multitasking built in. Okay, so I could have multiple jobs running concurrently, and I could switch between them based on when a job blocked. Okay, so they had 6 layers. The starting layer was layer 0, of course, because this is computer science. So Dijkstra started with layer 0 and went all the way up to layer 5. And each layer basically only interacts with the immediately, again, here we go, the layer immediately beneath. So yeah, you may have some of the highest layers interact with multiple, but generally you make each layer really self-contained. Okay? And so layers were heavily tested, and so these were the things that they noticed in their effort. Test layer I, at least some of layer I plus 1 has to be implemented. And they also found that they spent a lot of time planning the tests, writing the tests very carefully, making sure that they were useful, and then verifying the results. So very careful design process. Part of the reason why they had to do this is because they were designing this OS on another batch processing system. Remember all the stuff I told you about in the first few lectures? How did they test their OS layers? Here's my stack of punch cards. Here, operator, here's my stack of punch cards. I'll come back in 6 hours and find out the results of my tests. When you have that kind of turnaround, you're very careful about designing things. So you study everything very carefully because it's going to be a while. So very different development approach than we have nowadays, that we can get an answer instantaneously and go back and look at what we did wrong. Okay? I mean, sometimes if I'm not sure if something works, I'll just write it and then write the test and run it and see if it explodes or not. Very different kind of world than these guys lived in. Okay? Let's see. So yeah, abstractions, as you can see. So layer 0, multi-programming. So this is scheduling, context switch, stuff like that. You even have simple synchronization primitives, which tend to exist at this level. You have virtual memory built on top of that. Layer 2, communication with the console. Okay. Layer 3 was device I/O, including buffering. Wow, so we can actually buffer up stuff and write it out. Layer 4, user programs. Simple OS. This was research, so they basically had compilation, running programs, printing output, a few other things, but it was a pretty limited OS. Okay. And then 5 is the operator. I don't know why he padded his number of layers by including the user, but he did. Anyway, it was humorous in his research, but you can actually go find his research paper describing this. But this was the Eindhoven operating system implementation. You can see the layering and how everything was broken down. They found that they had a very, very small number of software defects in their code, okay? Which is pretty neat. That's a great result. The only downside is that it takes a long time to do this kind of stuff. And so this is always the issue that software development efforts have to wrestle with. How much time do I spend designing up front, which a lot of times by higher-ups is not perceived as work, because you're not coding. People think coding is work. But it turns out that it makes it very easy to identify issues quickly and resolve them quickly. So you're spending a lot more time up front to save time in the end. And so that may actually be really a good approach. Okay, the other thing that they noticed, large levels of abstraction. So I have all these layers, and each layer interacts with the layer beneath it, and that layer interacts with the layer beneath it. They found that this really reduced the OS performance. This is kind of an interesting issue, because we'll actually revisit this. There's been There's been a lot of focus about how do you deal with performance issues introduced by better abstractions in OSs. Okay, you see this pull between, I want to have a clean implementation that's easy to debug and easy to figure out where responsibilities lie, and I want it to be really fast and efficient. Those two things are at odds with each other. So this was a big issue. Okay. So one approach that they proposed was just have fewer layers, and each layer is fatter. And ideally, then you have less interaction between layers, and so that'll improve the performance. Okay, but there's the layered structure. Are there any questions? So that's that. Last one that I want to talk about today. There's a really interesting issue that we have with monolithic kernels. Okay? You guys you probably have always lived in a world with modular kernels. Linux is a modular kernel. Windows is a modular kernel. People say this. Back when I was a frosh, we didn't have a modular Linux kernel. We compiled everything into the kernel. And so you kind of would notice this issue that the kernel would be really large because you need to support a whole bunch of different devices. So if you're going to support the device, you have to have the device code in the kernel, which means it's got to be compiled in there. Okay? So if I want to add a new device, well, I have to add the code to the kernel code, recompile it, and then I support the device. We had to do this all the time. I got a new sound card. I want to be able to, make sounds on my computer. I've got to recompile Linux with the sound driver in the kernel so that I can interact with the sound card. Okay? So annoying. Okay? So, a couple issues. One is that the kernel becomes gigumongous because you're compiling all of this code into the kernel just to support drivers, just to support file systems and so forth. And you may not actually need all of that stuff. Okay? So more code almost always means more bugs. That's a really good rule of thumb. Shrink code, you're going to have fewer bugs. Okay? So basically what people started doing is figuring out how to modularize the kernel. Okay? So I can now say, I need this module, I'm going to load it, and I'm going to link it in at runtime so that it is now part of the kernel code. Okay? This is really cool. And you'll notice that this is called a modular kernel. Modular kernels are also monolithic, but they're nicer. Okay? So it tends to be you still have a lot of global variables. You still have everything can talk to everything else. You have a slight increase in modularity because a modular kernel can say, I have private symbols. Don't let anybody else see them. But the public symbols, everybody can see. So you don't have a lot of constraints that way. So, but these solve a lot of problems. Okay. Now there will be certain things that are always included in the kernel, like I have here, scheduling, virtual memory, and so forth. And then the kernel will simply define interfaces for things that may need to be modular. File systems, block devices, character devices, things like that. Okay. And so then there's also a module loader, which is basically a linker, but it's built into the kernel so that it can load a module, take a symbol table, hook things up by address, and then that code, you're basically injecting code into the kernel, which has its own exciting and scary aspects to it. Okay? So it's a pretty neat idea. Any questions about this? This is how basically all of our current operating systems work. I should say the ones that you probably have contact with day to day. OS X works this way extensively. Linux works this way extensively. So now I want to have a sound card where you plug it in and you say insmod and the module's loaded into the kernel and now I have sound card support. I don't have to rebuild the kernel. Okay, yeah, so you get the high performance of monolithic kernels. You can control what you expose. I talked a little bit about that. You get a smaller monolithic kernel, basically. You only have the code loaded that you need. Okay? Drawbacks? Well, guess what? You still have the downsides of monolithic kernels. They're still more brittle than the alternative, which we'll talk about next time. And these modules are running in kernel mode, which gives you a great amount of power. You can actually load a kernel module and touch a lot of things that maybe you shouldn't. And so whoever provides these things, it better be trusted. Like Linux, where you have, just get some code and compile it, and now it's a kernel module, and I can load it into my OS. Obviously, the ability to do this is constrained, but it would be really easy to inject malicious code into a kernel using this mechanism, if you're not paying attention. Okay, yeah, so that's basically saying the same thing as I did last time. Okay, so these are things that I'm going to, so this is just to make sure you understand. Monolithic is basically how much code. Modular is how do you manage it. So modular kernels are frequently monolithic. Not all monolithic kernels are modular, but nowadays most of them are. Okay, so let me see. One last slide. Yeah, so next time we'll talk about the cool wave of the future and the past with microkernels. So we'll see you next time.